In the last lecture, we were examining unidirectional transport, unsteady unidirectional transport in a spherical coordinate system as an example of a curvilinear coordinate system, where surfaces of constant coordinate are curved surfaces. In this particular case, this spherical coordinate system is used for solving problems in geometries that have spherical symmetry. For example, the heat transfer around a spherical particle or the mass transfer from a spherical drop or such problems. And in this case, one of the coordinates is the distance from the origin. The origin is fixed at the center of the particle or the drop, and the one of the coordinates is the distance from the origin. And these have spherical symmetry, that is, at a fixed distance from the origin, the concentration or the temperature field or the field variable is independent of orientation of the position vector. Okay. Therefore, it is spherically symmetric, that is, on a spherical surface, regardless of location on that surface, the concentration or temperature is the same. That is for problems that are spherically symmetric. And for such problems, we can assume one of the coordinates as the distance from the origin. Okay. So, we constructed a differential volume in a spherical coordinate system. The differential volume is bounded by two surfaces of constant coordinate separated by an infinitesimal distance. Two surfaces of constant coordinate at r and r plus delta r separated by an infinitesimal distance delta r. The surface areas of the surfaces at r and r plus delta r are given by these. Note that the surface area increases as r increases, and the volume is given by 4 pi r square delta r. And we had done the balance the usual way. Change in mass in time delta t is equal to mass in minus mass out plus the production of mass in the differential volume. The mass in at the surface is due to the flux in the plus r direction at the inner surface, gr at r times 4 pi r square. This is into the volume and it increases the mass within the volume. Similarly, mass out at the surface at r plus delta r is in the positive r direction. Therefore, that mass out is gr at r plus delta r times 4 pi r plus delta r square. And note that the surface areas are different, okay, at the surface at r and the surface at r plus delta r. So, substituting this, dividing by the volume 4 pi r square delta r and dividing by delta t, we get the differential equation, okay, where gr is the flux. The left side is the rate of change of concentration, the right side is minus 1 by r square d by dr of r square times gr plus the volumetric source. Substitute the equation for the flux from Fick's law for diffusion, gr is equal to minus d times partial c by partial r, and we get this differential equation for the concentration field. If the diffusion coefficient is a constant, it simplifies, because you can take the diffusion coefficient outside of the derivatives. Okay. So, this is for a constant diffusion coefficient. We were examining steady solutions. Okay. In the earlier lecture, we were examining steady solutions, where 1 by r square d by dr of r square dt by dr is equal to 0. Okay. And if you recall, okay, I had said that the temperature field, okay, T minus T infinity is equal to T naught minus T infinity into R by R. Okay. This satisfies the boundary condition that T is equal to T naught at R is equal to R on the surface temperature is T naught, and T is equal to T infinity for r going to infinity. The heat flux Qr is equal to minus k partial T by partial r. Okay. You can easily differentiate this. Okay. So, you will get minus k into T naught minus T infinity, okay, r. When I take the derivative of 1 over r, I will get minus 1 over r square. So, this actually becomes a plus by r square. I had done it last time for you in dimensionless variables. Here I am doing it in dimensional variables. That is the only difference. We will end up with the same result, and that is that the total heat transfer rate has to be equal to 4 pi r squared times Qr. The heat transfer rate out of a surface of radius r. Okay. If I take a spherical surface of radius r, okay, if I take a spherical surface of radius r, the heat transfer rate out of that surface is 4 pi r square times Qr, because the heat flux Qr is in the radial direction, okay, at all points. Okay. It is in the direction of increasing r, okay, the heat flux at all points. Okay. Therefore, this is 4 pi r square times Qr, and this is equal to k into 4 pi k into T naught minus T infinity to r. And from this I can relate the temperature difference to the total heat transfer rate. Okay. I can relate the temperature difference T minus, okay, between the surface and the ambient to and if I substitute that in here, okay, if I substitute that in here, I will get Q by 4 pi k r. Okay. This is Qr, the heat flux in the r direction. So, T minus T infinity, okay, T minus T infinity is the temperature at some location r, okay, at some location r from the origin minus the background temperature, okay, the temperature difference between the surface and the ambient. Okay. T minus T infinity is only a function of Qr. Okay. So, therefore, even if I had this T minus T infinity at the location r, as per this expression, is independent of the radius of the sphere. Okay. So, if I had spheres of different radii, so long as the total heat transfer rate or the heat generated by the sphere per unit time, so long as that is the same, the temperature at a location r is going to be the same, or the temperature field is going to be the same. So, the temperature field outside of the sphere depends only upon the heat transfer rate, the heat generation per unit time by the sphere, okay, or the total heat transfer rate per unit time across that surface. Okay. The heat transfer rate is independent of radius, okay, as you can see over here. The heat transfer rate is independent of radius, even though the heat flux depends upon radius. Heat flux goes as 1 over r square, which means that the heat transfer rate, which is flux times surface area proportional to r square, is independent of radius. That is because there are no sources or sinks within the domain in this particular case. So, when the temperature is expressed in terms of the heat transfer rate per unit time, the total heat that is generated by the sphere per unit time, that expression is independent of the radius of the sphere. That means that it is also valid even for a point particle, okay, for a point particle whose radius goes to 0. so long as the total heat generated per unit time by that sphere is the same. Okay. So long as the total heat generated by per unit time by that sphere is the same. Okay. So, that is the concept of a point source. In the limit as the radius of the sphere goes to 0, if the heat generated by the sphere per unit time is a constant, then the heat transfer rate is a constant, and then the temperature profile is only a function of that heat transfer rate, not on the size of that particle. Okay. So, if I go to distances that are sufficiently large compared to the radius, the particle will appear like a point source. This concept of point source will become important later when we solve the diffusion equation. Okay. Now that we have the heat flux, right, we can calculate a correlation for the Nusselt number, for example. Okay. What is the correlation for the Nusselt number? Okay. The Nusselt number is equal to the average flux by K into delta T by the diameter. Okay. In this case, this is the average flux at the particle surface. Okay. This is the average flux at the particle surface. Okay. In this case, the temperature is axisymmetric, so the flux is the same at all points on the particle surface. So, this is equal to the radial flux at r is equal to r divided by K into T naught minus T infinity by T. Okay. The flux at the surface can be calculated from here. Okay. QR at r is equal to r has got to be equal to K into T naught minus T infinity r by, I am sorry, which is just equal to K into T naught minus T infinity by r at the surface. Okay. By the diameter. Okay. Note that when we define these dimensionless groups, the characteristic length scale in that definition is the diameter. Okay. So, this just gives you 2, okay, because the T naught minus T infinity and K will both cancel out, okay, and I just get the ratio of the diameter and the radius. Okay. This gives me 2. Okay. So, this is the Nusselt number for heat conduction from a particle, okay, the correlation for the Nusselt number, which we had specified earlier, we have now derived it over here, okay, the correlation for the Nusselt number from a particle. Okay. So, from the spherical particle, the Nusselt number is 2, the Sherwood number is 2, okay, for mass transfer. Okay. The calculation is exactly the same. So, this is the Nusselt number correlation that we have obtained. Okay. So, let us consider a slightly more complicated problem, which is the conduction from a spherical shell. Okay. So, let us say that I had a spherical shell between two spherical surfaces okay, concentric spherical surfaces, okay, with inner radius r I and outer radius r o. Okay, inner radius is r I and outer radius is r o, and the temperature is on the inner surface T equals T I, on the outer surface T is equal to T O. Okay. So, I have to solve the differential equation 1 by r square d by dr. In this case, it will be a total derivative because it is steady. with the boundary conditions T is equal to Ti at R is equal to Ri and T is equal to To at R is equal to Ro. And I can scale the coordinates. Okay, I can scale the coordinates. In this case, I will just take the scaled radius as R by Ri, for example. Okay. Okay. And okay, T star is equal to the difference in temperature between a location and the temperature at the inner and outer surfaces. Okay. Okay. Since T star is linear in T, the equation remains unchanged since R star is also linear in R. Okay. So, the equation becomes 1 by R star square d by dr star of R square dt by dr is equal to 0. Okay. And the boundary conditions are okay, T star is equal to 0 at R star is equal to 1 and T star is equal to 1 at R star is equal to the ratio of the radii. Okay. Note that R star is equal to the radius divided by inner radius in this case. That is the convention that we have adopted here. Okay. So, therefore, T star is 0 at R is equal to 1 and T is 1 at R is equal to Ro by Ri. Okay. So, the equation can be now easily solved. Okay. The equation is actually the solution is the same as what we had earlier. T star is equal to A by R plus B. Okay. And this A and B have to be determined from the boundary conditions. Okay. I will not go into the calculation here, I will just give you the result and it will become obvious that this is the solution. This is equal to 1 minus 1 by R star by 1 minus Ri by Ro. Okay. Okay, that is the solution. Okay. At R star is equal to 1, at R star is equal to 1, you can verify T star is equal to 0. At R star is equal to Ro by Ri, okay, at R star is equal to Ro by Ri, you can verify that T star is equal to 1 as required by the boundary conditions. And this is of the form a constant divided by R star plus another constant. So, it satisfies the equation, it satisfies the boundary conditions. Therefore, this is the solution of the equation. Okay. Or alternatively, if I want to express it back in dimensional form, okay, I will get T minus Ti by To minus Ti is equal to 1 minus Ri by R by 1 minus Ri by Ro. Okay, that is the equation. I can get the flux QR is equal to minus K into partial T by partial R. Okay, that is the flux QR. Okay. Okay. Into in the numerator I have the derivative of 1 over R, okay, that is minus Ri by R square, okay, that is divided by 1 minus Ri by Ro. That is the flux. Okay. Okay. So, this will be equal to minus k into To minus Ti, okay, and I divide the numerator and denominator by Ri. Okay. So, therefore, I will get R square into 1 by Ri minus 1 by Ro. Okay. That is a flux QR, okay, from any surface. So, you can very easily verify that if To is greater than Ti, okay, if To is greater than Ti, that means that the heat flux has to be negative, it has to go inwards, okay, and this satisfies that, because 1 over Ri is greater than 1 over Ro. Okay, let me write this carefully. Okay. So, the heat flux has to be opposite to the direction of the temperature difference, okay, and this satisfies that. The total heat transfer rate Q is equal to 4 pi r square times QR is equal to 4 pi into k, negative sign, minus 4 pi k into T naught minus Ti by 1 by Ri minus 1 by, okay. Note that the denominator is positive, okay, because Ri is less than Ro, Ri is the inner radius and Ro is the outer radius. Therefore, Ri is less than Ro, which means that the inverse is greater, Ri inverse is greater than Ro inverse. So, that is the total heat transfer rate, okay, QR. And if I express it in terms of the temperature difference, okay, this QR, if I express it in terms of the temperature difference, Q is equal to minus 4 pi k into delta T. Okay. You recall that we had defined the heat transfer resistance. Okay. The heat transfer resistance is equal to minus delta T by QR. For the heat transfer in a particular configuration, we had defined the heat transfer resistance as the difference in temperature divided by the total heat transfer rate. Okay. And that heat transfer resistance, in this case the difference in temperature by the total heat transfer rate, okay, is equal to 1 by Ri minus 1 by Ro by 4 pi k. Okay. So, this is the heat transfer resistance in a spherical coordinate system. Okay. So, if you recall, in a Cartesian coordinate system, when we had done heat conduction in a Cartesian coordinate system, the resistance was equal to H by K A, okay, H by K A, okay. Okay, where H was the thickness of the slab. Okay, so, the H was the thickness and A was the area. Okay. And delta T was the temperature difference. Okay. Okay, that was for a Cartesian coordinate system. Okay. If you recall, for a cylindrical coordinate system, okay, with inner radius Ri and outer radius Ro, okay, the resistance cylindrical was equal to log of by 2 pi k L. Okay. Where L was the length in the direction along the axis, okay, and Rho and Ri were the outer and inner radii, and this was also the same as the outer and inner diameters, okay, the ratio of those two. Okay. And this is for a spherical coordinate system. The resistance, okay, in a spherical coordinate system is equal to 1 by Ri minus 1 by Ro by 4 pi k. Okay. In all cases, the resistance go as 1 over k and 1 over distance, okay, in all these cases. Okay. So, therefore, in the spherical coordinate system, if I had, for example, a series resistance, okay, if I had two concentric cylinders, okay, the total resistance will be the resistance of the first plus the resistance of the second. Okay. And for each of these first and second, you will have an inner and outer radius. Okay. So, for each of these, you take 1 by Ri minus 1 by Ro by 4 pi k to get the resistance of the individual, okay, spherical shells, okay, and then add up the resistance of these individual spherical shells in order to get the total resistance. Okay. And once you do that, you will find that the total delta T, okay, delta T across the whole thing, okay, delta T across the whole thing is equal to the resistance of the first plus the resistance of the second into the total heat flux. Okay, delta T is similar to a voltage difference, Q is similar to a current, and therefore, the ratio delta T by Q, it should have a negative sign because heat transfers from higher to lower temperature. This will be equal to minus of the sum of the resistances times the total heat transfer rate, okay, not the heat flux, the total heat transfer rate. So, this is the equivalent of heat transfer resistances for a spherical coordinate system, for a spherical shell. Okay. If you had multiple shells, you will just add up the resistance of each of those shells, okay, and the resistance of each shell is given by this expression. Okay. So, this completes our discussion of heat transfer at steady state. Okay. I solved the heat transfer problem for you for an infinite domain first, for heat conduction from a particle, and then second I solved this for you in a spherical shell. Okay. So, next we will proceed to heat transfer, unsteady heat transfer, before we complete the discussion of unidirectional flows. So, I will solve some problems in unsteady heat transfer in the next lecture before we go on to pressure driven flows, which is the next topic. I will continue this in the next lecture. I will see you then.